Hello. My agenda today is, after first introduction, I give you a specification overview about CAN safety, and I talk a little bit then about future requirements, and in the end we can have the discussion questions. For introduction, my name is Koppe. My technical background is I studied electrical engineering, and I'm head of engineering at the company Microcontrol. And just in case some of you remember my face and say, hi, I've seen this guy before. Yes, that's maybe the reason because I was technical director of the CAN automation until April 2023. Shortly about our company, Microcontrol has within its product portfolio, we have 4 pillars in our product portfolio. That is mainly I/O modules and control systems, PLCs, but also protocol stacks based on CAN Open, J1939, and we offer services. But let's jump directly into the topic, and let's say, take the ball from Mark about this CAN safety, and I put now the level a little bit higher to the higher layer protocol, and this higher layer protocol is CAN safety. So what you see here is the relationship of this CAN safety standard in conjunction with other standards. And this picture is a reference from the EN 5325-5, and this specification, this EN specification, that is our CAN safety. So when I talk about CAN safety, especially to customers, I sometimes feel like a butcher, or like in the UK you say the butcher. So why I'm saying this? Because typically for the butcher, the customer comes into my store and says, hello, I have a garden party next week and I need 10 pounds of meat. And as a butcher, I answer, well, I can offer you beef, lamb, pork. You want to buy it as a whole, or shall I cut it into pieces? Yeah, you take my offering, take the meat to your garden party, and 3 days later I get a call and you say, okay, I have a problem because I have no music, no drinks, no salads, and the meat is still raw. Yeah, because I'm a butcher. I'm not somebody who is offering you the whole stuff for a garden party. I'm not a cocktail mixer. Saying this with this example is, if you're starting to do a project for safety, then it's not sufficient to only to say, I take the specification for CAN safety, these EN 5325-5, in order to have a safety product afterwards. You need more than this. You need all these other specifications shown here, and this is a complete process. So take this as an example. The CAN safety stuff is only the meat, and it's still raw, and you have to put it on a grill and do a lot of things more in order to have a garden party. So if we are talking now about the meat in the next couple of minutes, so we have some more CAN safety related specification than only this EN 5325-4. -5. The -4 is the industrial communication subsystem based on CAN. That's the title, and that is the classical CAN Open. And our CAN safety is based on classical CAN Open. And you see this, I highlighted here this CC because that is that's the actual standard. We still rely on classical CAN Open and classical CAN, which means we are limited to a payload of 8 bytes, not more than this. When using CAN safety, which was former a CiA standard 304, this is not always then sufficient to start with that, because you implemented devices. You're, for example, implementing an encoder, an inclinometer, or a drive. And then, in order to do so, you have to do an additional look into that specification, because they have extra parts in order to implement these safety functionalities, especially for those device profiles. And in addition to that, there's also a specification, CiA's 319, which gives you some implementation hints in order to set up your safety-related device. So now when we are talking about CAN Open Safety, we have this kind of block diagram where we have two so-called SR devices, safety-related devices, which communicate with each other via a CAN network. So you can see here there is a blue part, which is a non-safety logical device, and there CAN Open services like PDOs, which can be used in parallel to the safety communication. And at least, of course, we need two safety-related devices. Just one does not make sense in such kind of a network. What we also see here, that for this safety communication, we have these so-called SRDOs. These are so-called safety-related data objects. I explain them in detail later on. And in order to use them, we have to configure them also in a safe way. In order to achieve this safety, and that is, let's say, also what Mark just explained, we have kinds of communication errors like corruption, unintended repetition, incorrect sequence, loss, and so on. And we have to do some safety measures in order to be sure that we don't run in these kinds of situations. And there is a safety measures matrix inside the specification, which explains what measures are taken in order to avoid these to detect these kind of communication errors. So what is the principle? The basic principle in order to do a safety-related communication is to use these kind of safety-related data objects, and the principle is that we are using two CAN frames for that kind of a communication. And we're doing this communication in a cyclic way. So we have a cyclic transmission. We are transmitting CAN frames two times, a CAN frame number 1 and a CAN frame number 2, with the difference that CAN frame number 2 has its data payload bitwise inverted to CAN frame number 1. In addition, there is a certain time between CAN frame number 1 and CAN frame number 2, and we have a refresh time. So always these two packets are sent via the bus with a so-called refresh time, with a repetition time, and we have a certain time between those two frames. From the receiver's point of view, the receiver checks, first of all, that their first frame is CAN frame number 1 and the second frame is CAN frame number 2, so that they are not interchanged during transmission. That this so-called safety-related validation time between these two CAN frames is still within the limits. And of course, that this overall repetition time, this so-called safeguard cycle time, is still valid. So this is the principle for the communication between a producer and a consumer. In order to do so, within CAN Open Safety, it has been decided to take pretty much the same approach that we have for the well-known PDOs, for the process data communication, with the difference that we here, with PDOs, we only have one identifier, one so-called communication object identifier here in that parameter view. These are the subindex 5 and 6. Within PDOs, we only have, as I said, only one, but for SRDOs, we need two. So we have two identifiers which need to differ. There's a rule for that, so that the first one has an odd value and the second one is an even value. In addition, we have a fixed transmission type here. So this is always based on time. Unlike the PDOs where you can say they are event-driven or send via a sync message. This is not possible for SRDOs. They always send on a cyclic base. And the next limitation for SRDOs is that we are only limited in a total to 64 SRDOs in a complete networks. This, of course, also limits our number of total data that we can share within this kind of network. As a comparison, PDOs, we can have up to 512 transmit PDOs and 512 RX PDOs. So there's a certain limitation also here in the numbering of safety-related data objects. As well as for the communication, we have the same approach here, as I said, for PDOs, here with the SRDOs, also for the mapping parameters. Whereas here, as we need 2 CAN frames, we need to map data 2 times. First, the normal, let's say normal non-inverted value, and the second is the bitwise inverted data value. So that means that also here our mapping table compared to what we know from PDOs is a little bit different, because we have to map 2 objects always. So subindex 1 here is the first data object which is mapped, and subindex 2 is the inverted data object that we have to map if we want to use variable mapping during configuration. The value which is mapped there, this unsigned 32-bit value, is pretty much the same like for PDOs. So if you're known to classical CAN open communication, nothing changes there for you. Now, the next step, what you have to do then for safety is the safety configuration. Because just saying, I have got now a safety protocol and these 2 SRDOs, and maybe everything is already pre-configured, and then through some magic, it just starts. No, that is not the way how it works. So what you have to do in order to get things up and starting is you need to calculate a CRC over all these SRDO communication and mapping entries. And it doesn't matter if you do that and if you configure that during the configuration phase, or you leave them unchanged and say, I don't care, I'm happy what has been pre-configured by the device manufacturer. You have to do this calculation with a certain CRC algorithm, which I will show later on. Take this 16-bit CRC value, write that down to the device, and write a configuration value or valid also into the device. As a result, the device checks and says, is that CRC value that I've been assigned to from the outside tool or from the outside CAN manager, is that valid or not? And if not, it doesn't react at all, and it stays still in its safe state. If everything is okay, then this safety-related device may now leave the safe state. So you have a certain kind of configuration phase that you have to take into account when you deal around with CAN open safety devices. In addition to that, there's a so-called global failsafe command, which any device in the network can send, and this uses the identifier 1, so very high priority without any data, with a data length code of 0, and that can be used to get all devices, safety-related devices within the network into a safe state. And this, from the device's point of view, this also can be supervised via an object in the object dictionary. As I already mentioned, within the specification, there is a requirement to calculate a CRC signature over the SRDO structure. And here in these slides, I haven't taken the approach to use this pseudocode there and with this mathematics there. I just used a C code structure in order to show which parameter values we have to take for them for this calculation. And here's the calculation of this CRC signature with the according polynomial. And this one has to be taken in order to get, as I already said, to get this device into this mode that it gets out of the safe state. Now, if we look into the problems that we might have when we look to the current version of this standard, that is from my point of view, from the point of the view of the butcher, which wants to provide you good meat for your next garden party. When I have a look on that existing specification, then I see there we have some outdated references in there. So first of all, there's a reference to specification GSET26. It has been withdrawn in the meanwhile. The next point is there in the annex, there are some models reference which I will address later on, which also come from this withdrawn specification. And then there is a nice sentence there in chapter 9.4.2 of this specification saying something about the residual error probability for SRDOs. And this original wording I've referenced here, and it says the worst case residual error probability is squared according to this GSET26 for the use of model 3 as shown in formula number 5. The other modules may be used, but then it shall be shown that the following formula is still valid. And they say here something about the residual error probability, which is equal to the square probability of CAN, which is equal to 4.9 multiplied by 10 powered by minus 17. So first of all, from the mathematical point of view, the equal sign is not a good idea. The second point is what we see later when we have a look to the model. This may lead to the consumption for the customer of the meat that the meat can only be used on a gas grill, but nothing else. I will explain later. The next topic that I have seen beside that is missing security. That will be the next speaker is Olaf, who will tell something about security, because the point here is when we're talking about safety, safety is always somehow related to security. And then we have still now, until now, no secure approach in order to verify that the data which has been written is from a device that we trust. So that is the point. There is a let's say an encoder which is put out of the safe state in the working state, and there is no way for that encoder to make sure that the guy who communicated with him is the right one and not a bad guy, a kind of man in the middle attack. And last but not least, my last point is I've already said that we also need the safety approach also in device profiles. And I've mentioned 3 of those device profiles, but we have much more within the CANopen family. So where are there these safety integration in these device profiles? Yes, they are missing. So they are still not there. And if somebody says, I need for a generic IO device, I need safety, is alone in the field. So let's come to this modules issue from Annex A of this specification. So we have got 4 models which are in the annex, and as I said, they are from these withdrawn specifications, and their models are numbered model 1 to model 4. So the first model they refer to is also an approach that we have just seen from Mark, where he said, okay, we could have 2 CAN controllers or so-called safety communication layers here, 2 data link layers, 2 physical layers, and they are both connected individually to an individual CAN bus in order to have some kind of redundancy. So wait a second here. When I say redundancy, I'm talking about redundancy in forms of communication. And that means we have a specific standard for that within CANopen, and which is totally another approach. Because if maybe you are more related to safety and talk about redundancy, you want to make sure that with your redundancy, if you detect an error, that you go in a safe state. Whereas from that point where we have this redundancy specification within CiA using two distinct CAN wires, we say if we detect one error, we don't care. We just run the communication over the wire which is not affected. So these are totally two different things from the point of viewing. So we don't have to mix that up, especially this wording redundancy. I'm always asking customers what we are talking about there. Model number 2 then says, okay, we don't, or starting with model 2 says we don't take two CAN wires because it's of course more cost effective to use only one CAN wire, but still using two CAN controllers, two data link layers, two physical layers. Keeping this in mind, and also coming back to model number 1, this drawing might imply that you're using two CANopen state machines there, which is not true. And that means this drawing shall not tell you you're using two node IDs. I'm just saying that because I've already seen that in the market, that people say, I have got a safety device and it's safe because I have got two microcontrollers in there, two physical layer transceivers in there, and two different node IDs. Everything is separated, and that is safety. That is not the intention from the communication point of view of CANopen, because typically CANopen safety expects that you only have one node ID that you can configure. So please keep in mind that this drawing here in model 2 and 3 and 4 always means you're talking always to one node ID. Coming back to model 2, that says you're sending this SRDO via the frame number 1 from the first node, frame number 2 from the second node. Model 3 and model 4 merge these physical layers and data link layers more and more together. So in the end, it's your choice in order to use any of the approaches. But please keep in mind that this sentence is there still in the specification. And most people think, oh, I can only be happy with model number 3 if I take that for my actual approach. As I already said, if we're talking about CANopen safety, it's not only to use that for the communication part for the SRDOs. We have to consider also the implementation in the device profiles. And I've taken here as an example a drawing from the specification for encoders from the CiA 406. So typically there you have got a value for a position value, or maybe a high resolution position value, or a speed value, and things like that. Now what you have to think about it, if you already have a kind of encoder, then you have to double these kinds of process values, because you then also need inverted values for all these process values that you already have, because you have to map them first of all, and second you have to secure them. So you have, in the same way like I've shown before with the CSC procedure for the SRDOs, you have to do the very much same procedure for all these values for an encoder or whatever device you have, because you have to consider that the end user can change parameter values within the device. Then the communication as such is safe, but the data which is transferred has been modified by somebody, by the bad guy, by me, or whosoever. Because we have, let's say, these kind of problems and visions within the Canon automation, we have called for a meeting for an inaugural starting of the group, of a new group for functional safety. This was end of January this year, and here are the results of this meeting. So first of all, as a surprise, especially for me, as the audience said there, we don't have requirements for CanFD or even CanOpenFD or CanXL, which means people said, we want to stick to classical CanOpen. The outcome also was that this specification may need formal updates. I would say, yes, it definitely needs formal updates. We need also to think about security considerations. That will be the next topic from Olaf when we're talking about security on CAN. Maybe we could use also a running number inside these SRDOs. And we were also thinking the outcome was about thinking about a future protocol. Maybe it's a nice idea to support routers, maybe to use black channel, maybe to support security features, maybe to support, beside classical CanOpen, also FD and CanXL. My point of view at this stage is we have to think about CanFD and CanXL because it's really a pain in order to get security or these things that we need to do just simply with classical CAN. So as an outcome, a new working group was started, this IG 06601 for functional safety. Here's the scope of this working group. It's the development and maintenance of CAN-based functional safety protocols, including higher layer management. This includes in particular the CanOpen safety protocol as specified in that EN 5325-5. And that means for me, it's an invitation for all of you. If you're involved in safety and in security, please join this group because we need you in order to take the next garden party as a success, because otherwise you're getting fish or vegetarian food. Thank you.